Good afternoon, ladies and gentlemen. Welcome to today's special lecture on manipulating atoms with light, the review of a few promising applications by Professor Claude Cohen-Tanoudji. First, I would like to invite Dr. Tuisak Goanantagun to address the welcoming remarks.
Professor Cohen-Tanoudji, Inspector General, Ministry of Science and Technology, distinguished guests, ladies and gentlemen. On behalf of National Electronics and Computer Technology Center, or NECTEC, I have the great privilege and pleasure to welcome Professor Claude Cohen-Tanoudji, the Nobel Laureate in Physics in 1997, and the distinguished guests to the Knowledge Mart Special Forum with the theme of Nobel Prize Lecture Series. I am delighted to have the presence of Professor Cohen-Tanoudji and to have his opportunity to host this distinguished forum. I do sincerely hope that beside the substantial and fruitful discussion that we anticipate at this forum, you will have enough time to enjoy what Thailand, Bangkok has to offer during the holiday festival. I'd like to thank the International Peace Foundation for facilitating the arrangement of this meaningful meeting today. National Electronics and Computer Technology Center, on behalf of the Ministry of Science and Technology, recognizes the importance of knowledge and information sharing on science and technology, which would have significant implications towards ideas and innovation. Therefore, in cooperation with the International Peace Foundation, NECTEC is most honored to arrange the series of Knowledge Mart Special Forum with Nobel Laureate. As you may all know that the Nobel Prize is an international award given yearly since 1901 for the achievement in physics, chemistry, medicine, literature, peace, and economic to a world prominent breakthrough of discovery and innovation. All the works and discoveries are being recognized as world-renowned inventions, which have a great and important contribution to knowledge in its respective subject. Basic laser cooling and trapping of atoms, led by Professor Stephen Chu, Professor William Phillips, and Professor Cohen, is the key fundamental for new discoveries. These include the new state of matter, so-called Bose-Einstein condensation, atomic interferometry for gravitational measurement, and the atomic lithography for next-generation atomic transistors, to name just a few. With the distinguished guest speaker leading this forum, I am confident that the fruitful lecture of Professor Cohen-Tanoudji and discussion today will be a great inspiration to our scientists and researchers for their best effort in technological research, development, and innovation in the long run. Thank you very much.
At room temperature, the air around us consists of around 25 trillion molecules in each cubic centimeter, and each of these atoms or molecules are moving in different directions at the speed of about 500 meters per second. So, if we want to study these individual atoms or molecules, how do we do that? We must at least slow them down, and then if we can do that, we will be able to open up the new era of control and study of atoms and atomic gases, which will lead to more advanced applications. It is my great pleasure and my privilege to introduce Professor Claude Cohen-Tanoudji. He was born in 1933 in Constantine, Algeria, which was then part of France. In 1962, he received a doctoral degree in physics from the École Normale Supérieure in Paris. He was appointed as a professor at the Collège de France in 1973. Among many books he authored the quantum mechanics books, the classic book that many of us, including myself, have used in school when we took quantum mechanics classes. And among other awards and distinctions, he received the 1996 Quantum Electronics Prize from the European Physical Society for his pioneering experiments on laser cooling and the trapping of atoms. And in 1997, he was awarded the Nobel Prize in Physics jointly with Professor Stephen Chu and Dr. William D. Phillips for the development of methods to cool and trap atoms with laser light. Please welcome Professor Claude Cohen-Tanoudji.
And I would like first, before starting, to tell you that I'm extremely happy to be here in this research center, wonderful research center, and to have this opportunity to meet many colleagues and friends here. And I'm happy this is my first visit to Thailand, and I'm extremely happy to be here and to have this opportunity to visit this beautiful country. So what I would like to discuss in my lecture this afternoon is the manipulation of atoms by light. So what I would like to do is to address a few questions. Then I would like to discuss how does light interact with atoms and introduce the basic quantum ideas about the energy levels of atoms and the basic emission and absorption processes of photon by atom. Then I would like to ask an important question: can one use this interaction? Can one master this interaction for getting information on atoms and for manipulating them, for controlling their various degrees of freedom? And I would like to give two examples: optical pumping and laser cooling. And finally, I think it's important, I would like to discuss what kind of new application can we find from these studies, new research fields, new devices which can be derived from these basic studies. So let me start with light. We all know, of course, that light is an electromagnetic wave consisting of an oscillating electric and magnetic field propagating in free space with a very high velocity, 300 kilometers per second. And the frequency of oscillation is nu. The period is 1/nu. And at a given time, light is represented by a sinusoidal wave with a special period, which is the so-called wavelength. And as all wave phenomena, light gives rise to interference and diffraction effect, which I can explain briefly here. Of course, I'm sure that you all know that. If you have a light source, S, a screen with two slits, an observation screen, and if we look at the intensity of the light which is observed on the observation screen, if you took a given point, M, light can follow two different paths from going from S to M, SEM or SBM, and depending on the point M in the screen, the two waves arriving in M can be in phase, oscillating phase, in which case the amplitude will be doubled, or out of phase, in which case will interfere destructively, and the total amplitude will be 0. So that if you plot the intensity as a function of the position here, you get maxima and minima, which are the well-known interference fringe, the Young fringes. But that well-known. But at the beginning of the last century, it appeared clearly that light is not only a wave, but also a set, an ensemble of particles called photons, having an energy E and a linear momentum P, given by this well-known Planck-Einstein relation, which tells you that the photons associated with the light wave with frequency nu have an energy E and a linear momentum P given by this equation, E equals h nu, P equals h nu over c, where nu is the frequency of the light, c is the velocity of light, and h, a basic constant of physics introduced by Planck, Max Planck, in the beginning of the previous century, 1900. And the important point is that both wave and particle aspects are essential. You cannot explain everything in terms of the wave only or the particles only. You need both aspects, and this is what is called wave-particle duality, and which is a very important concept in modern physics. Now I describe light briefly, because I'm sure that you all know a little this concept. Let me go to atoms. Atoms consist of electrons, which are small light particles with a negative charge, orbiting around a nucleus which is much more massive with a positive charge. That's the planetary model. If you take this model seriously, then you see that an accelerated charge should radiate energy in space, and the electron would progressively fall into the nucleus. And because the frequency of the motion of the electron is changing in time, the spectrum of the light emitted by the electron should be continuous. So the prediction of classical mechanics is that atoms should be unstable, and the light emitted by an atom should have a continuous spectrum. But that's not true. Atoms are stable, we don't collapse. And the light emitted by an atom, when you analyze this light with the spectrometer, you find a discrete series of frequencies. The light emitted, the spectrum is discrete. And to explain that, you need quantum mechanics. And the first step for quantum mechanics was achieved by Louis de Broglie, a French physicist in 1924, who extended the wave-particle duality from light to matter. And de Broglie introduced the revolutionary idea that with every matter particle of mass m and velocity v is associated a wave, which is called now the de Broglie wave, with the wavelength lambda de Broglie given by lambda de Broglie equals h, the Planck constant, divided by m, the mass, times the velocity. A few months later, Schrödinger showed that more generally the state of a particle, of matter particle, is described by a wave function, waves in space, obeying the well-known, the famous Schrödinger equation, which explains practically everything in a microscopic domain. And the important point is that when you try to solve this equation mathematically, you find that only certain solutions of these equations are physically acceptable. And you find, for example, discrete oscillation frequency is the same thing as when you take a string of a violin, of a piano. This string can oscillate only at certain frequency, which are the resonance frequency of this string. And that introduced in atomic physics the basic idea of quantization. For example, if you take the wave function describing an atomic electron moving in the potential of the nucleus, you find that only certain possible oscillation frequencies are possible, corresponding to well-defined energies of the atom. So that means that the energy, internal energy of an atom can take only discrete values, and you can represent these values by drawing a horizontal line, the altitude of which is proportional to the energies. This is the lowest possible energy level, the so-called ground state. This is the first excited state, the second excited state, so on. And you get what is called a spectrum of energy levels. Okay, now I've introduced the basic concept about light and atoms. I can describe now the elementary interaction processes between atoms and light and photons. And this process consists of emission process, where an atom initially in an upper state B can fall in a lower state A by emitting a photon h nu, that emission. The reverse process being called the absorption, where the atoms starting from a lower state absorb a photon h nu and go to the excited state B. And of course, you have a relation between h nu and the difference of energy between these two states, EB minus EA equals h nu, which just expresses the conservation of energy. When the atom goes from B to A, it loses some energy, and this energy is carried away by the photon which is emitted. To go from A to B, the atom needs to gain some energy which is given by the photon which is absorbed. Looking at this relation, you immediately understand that the principle of spectroscopy, because by measuring with the spectrometer the frequency of the line which are emitted by an atom, you can determine EB minus EA, you can determine the energy level structure. And the important point is that the energy spectrum, the set of discrete lines which is emitted by an atom, which are emitted by an atom, depend on the atom. They are not the same for hydrogen, sodium, rubidium. That means that the spectrum of line emitted by an atom is some sort of fingerprint of this atom, some sort of genetic print of this atom. So by looking at the light, which is emitted by a medium, you can identify what are the atoms which are emitting this light. Okay? And for example, all the information we have on the world, on the universe, the composition of the stars, of the planets, of the interstellar medium, of the galaxies, come from the measurement of the spectrum of the light which is emitted by this object. And also by looking at the Doppler shift of this line due to the motion, you can determine the motion of the astronomical object and prove that the universe is expanding. So you see that this shows you that light is a basic source of information on the world which surrounds us. Now, before going to the second point of view, which I would like to discuss in this lecture, light not only a source of information, but also a tool for acting on atoms, let me say a few words about the lasers. And let me go back to Einstein's work in 1917. Einstein, to explain the Planck law of blackbody radiation, was obliged theoretically to introduce two types of emission. The first one is spontaneous emission. When an atom is excited, it does not remain forever in the excited state. After a certain time, it spontaneously falls down to a lower state, but what is called spontaneous emission. It emits a photon in all directions of space. And the mean time spent by the atom in the excited state, E, is what is called the lifetime, the radiative lifetime of the excited state. It varies from one state to the other, from one atom to the other, but typically the order of magnitude of tau r is 10 to the minus 8 seconds, 10 nanoseconds. That is called spontaneous emission because it can occur even if the atom is alone, spontaneously decay. There is another type of emission which was introduced by Einstein in 1917, which is called induced emission or stimulated emission. And this process is the following one. If you have an atom in the excited state E, and if you send on this atom a photon h nu, which has a good frequency tuned to the transition E to G, this photon induces the atom to emit a second photon completely twin of the first one. The same energy, the same direction of propagation, the same polarization. Okay, so in other words, you have a second type of emission which is induced by an incoming radiation and which gives rise to photons which are exactly replica of the photon which induced this emission. That was nice, but people at that time considered this discovery as purely academic. What to do with that? Until that three decades after that, in the middle of the previous century, some new idea came out using stimulated emission, induced emission, and dealing with non-equilibrium medium. Let me remind you first what is a thermodynamic equilibrium. If you have an ensemble of atoms at thermal equilibrium with the reservoir, you can show that Boltzmann theory, you can show that a lower state, E1, is always more populated than a higher state, E2. The lower the state, the greater the population. That's the normal situation for equilibrium medium. But physicists started in the middle of the last century by collision processes, by interaction with light, by pumping light, to achieve what is called a non-equilibrium situation where the upper state, E2, can be more populated than the lower state, E1. Such a situation is called population inversion, inversion with respect to the thermal equilibrium. And in 1950, around 1950, Charlie Towns in the United States had the following idea. If we have a resonant beam, light beam, passing through a medium which is inverted, the new photons which appears by stimulated emission and which are identical to the incoming photons, and the number of which is proportional to the number of excited atoms, is bigger, is greater than the number of photons which disappear by absorption from the lower level, which is less populated. So you will have more new photons than photons which disappear. So after passing through the beam, through the medium, you will have more photons, so the light will be amplified. And that was a very important idea, that using inverted medium can be useful for amplifying light, for making what can be called amplification of light. And then from there, the next step was to take such an amplifying medium and to put it between two mirrors so that a light beam can pass several times, bounce forth and back between the two mirrors, and pass several times through the amplifying medium and be amplified each time. And if, of course, the mirrors are not perfect, after each reflection you lose a certain number of photons, you have some losses. But if the loss is smaller than the gain due to the amplifying medium, then the amplifier becomes unstable, like in electronics, and it becomes an oscillator. An unstable amplifier becomes an oscillator, and you get an oscillator for light. And that is called a laser light. Laser is an acronym from light amplification by stimulated emission radiation. And that was a big breakthrough, because laser light has completely new characteristics, much more interesting than usual thermal sources, like these lamps, more intense, more directive, more coherence, more brightness. A lot of new research fields have been opened. Physicists were now able, using laser light, to explore a new direction and a lot of new application, of course. You know, you all have a CD reader using laser light. You know that retina can be cured with laser light. You know that telecommunication can use laser light propagating along fiber. You know that you can cut material with high power laser. The number of applications of laser light is absolutely incredibly large. Okay, so let me now turn to the second point of view, which I would like to develop in this lecture: light as a tool for acting on atoms. The idea is to use resonant interaction between atoms and photons for perturbing atoms, for changing their state, changing their motion, changing their position. And in fact, to do that, you use the fact that when an atom absorbs a photon, the total energy is conserved, the total linear momentum is conserved, the total angular momentum is conserved. So you can use resonant exchanges of energy, angular momentum, linear momentum between atoms and photons for manipulating their degrees of freedom. And perhaps the first example I would like to give is the exchange of angular momentum between atoms and photons. And this is what is called now optical pumping, a topic which was discovered by my thesis supervisor, Alfred Kastler, who got the Nobel Prize in 1966 for this invention. So let me first remind you a few elementary facts about angular momentum of atoms. Atoms are objects which rotate. They are like spinning tops. You know, tops which rotate around itself. Atoms rotate around themselves, and they have an angular momentum g. And as all physical quantities, angular momentum is quantized. And if you look at the component gz of g along the axis z, the z-axis, you find that this projection is quantized. If I take the simplest possible example of what is called a spin 1/2 atom, one finds that gz, the angular momentum component along the z-axis, can take only two values, up or down. That's the quantization of angular momentum. You have only gz spin up or spin down. Because you have a rotation of charge, you have also a magnetic moment, mz, which is proportional to gz, and which can take only two possible values, magnetic moment up or down. Now, if you put this atom in a magnetic field, these two magnetic moment orientations have different magnetic energies, and you get two spin states, plus and minus, separated by an energy splitting proportional to the magnetic field, and which can be written delta E equals h Planck constant times a certain frequency, which is the frequency corresponding to this transition. And if you apply a radio frequency field with this frequency, you can induce absorption and emission process between these two states. And this is nothing but what is called in physics magnetic resonance. Magnetic resonance are absorption and emission process between two spin orientation. And of course, to detect magnetic resonance, you must have a different number of atoms in this state. In this state, the sample must be polar. You must have more atoms with a given spin orientation than with the other spin orientation. Now, if you take a sample of atoms at room temperature and in low magnetic field, the Boltzmann factor, which gives you the population difference, is very close to unity. You have a slightly more spin in the lower state than in the upper state, like ordinary thermal equilibrium, but the difference is extremely small. The polarization is nearly 50%, each 50% each state. So it's very difficult to detect magnetic resonance unless you have many, many spins. That means that magnetic resonance in low field and in usual temperature, when the Boltzmann factor is close to 1, can be detected only in dense systems, like liquids or solids. It's very difficult to detect it in gases, because the number of spins is too small. But then Kastler had the following idea. It's difficult to polarize atoms, but it's much easier to polarize light. And in fact, the photons which are associated with polarized light have an angular momentum. For light, the angular momentum of light the photon is related to the polarization of light. And it's easy to polarize light by using, for example, polarizers similar to those you have in your sunglasses. Okay? So you can polarize light, so you can have an ensemble of photons having angular momentum. And when atoms absorb these photons, they gain the angular momentum of the photon that they absorb. So by letting atom absorbing polarized light, you can polarize atom and reach degree of polarization nearly 90%. You can get high polarized atomic polarization. And then, if you have high polarization on gaseous samples, you can easily detect magnetic resonance in gaseous samples. And in gaseous samples, the interaction between atoms are much weaker than in dense systems, and you can get much narrower magnetic resonance curve and make much more precise determination of structure, magnetic structure. So that brought a lot of application, a lot of results. But I would like to give you an example of result which is very recent, about 10 years old, and which was unexpected, as often in research. 10 years ago, a few people had the idea of polarizing helium-3 by optical pumping. You know that helium does not hurt you because it's a rare gas. So if you mix polarized helium by optical pumping with air And if you have a patient breathing this mixture, the lungs are filled with polarized gas, and you can make what is called magnetic resonance imaging of the empty of the lung cavity, which is not easy to do because magnetic resonance imaging usually detects the magnetic resonance of the protons of the hydrogen atoms of the water molecules. So what you detect is actually the repartition of water molecules. You detect the solid or liquid parts of the body, the bones, the blood, the flesh, but you don't detect the cavity of the lung. Now, by filling the cavity of the lung with polarized gas, you can detect this cavity. And I show you the next slide, where you have two MRI pictures. On the left part, a usual proton MRI picture, where you see the coast, the stomach, the heart, the esophagus, but you don't see lung. And the right part, helium MRI, where you don't see the solid part, but you see now clearly the cavity of the lung. And that is developed a lot of places in the world, and it's now a new powerful diagnostic method for detecting lung disease like asthma, emphysema, lung cancers, the effect of tobacco, and so on. So I like this example because it shows you how important applications in physics usually are not planned in advance. That was not the result of a political planning, a program for curing lung disease. It came out because of a good basic research which suggested this idea which was completely unexpected before. Okay, so now I go to the second example of my talk, which is called light shift, and it was actually my thesis work in 1962. If the light which you use for exciting atoms is slightly detuned from resonance, you find theoretically and experimentally that the energy levels are shifted by light. So non-resonant light irradiation displaces the ground state G, and the displacement, which is here, which I call delta Eg, has a magnitude which is proportional to the light intensity, and a sign which depends on the sign of the detuning. If the light frequency omega n is larger than the atomic frequency omega a, if the light is detuned to the blue side, the shift is positive. If the light is detuned to the red side, if omega L is smaller than omega a, the light shift is negative. So by using non-resonant light, by choosing the detuning and the intensity, you can control the position of the ground state. You can change it as you want. So I go now to the third example of manipulation, which is now use the conservation of linear atom in atom-light interaction processes. I'm sure you have all seen a tennis ball hitting a racket. When it is hit, the racket recoils. You see also when a gun fires a bullet, the gun recoils. That's conservation of linear momentum. And that appears also when the atom emits or absorbs a photon. Let me consider an absorption process, an atom initially in the ground state, G, and a photon impinging on this atom with a linear momentum h nu over c. And the frequency chosen so that the process is resonant. So the atom absorbs the photon and goes to the excited state E. And the photon has disappeared. And the total linear momentum must be conserved. Initially, since the atom is at rest, the total linear momentum is equal to h nu over c. In the final state, the photon has disappeared, so the total linear momentum must be carried by the atom. So the atom must have a linear momentum, mv recoil equals h nu over c. So that means that the atom recoils. So when the atoms absorb a photon, it recoils with a velocity which is called the recoil velocity given by h nu over mc. Okay. Once the atom is excited, as I mentioned to you before, it does not remain in the excited state forever. After a certain time, it will emit light by spontaneous emission, the time tau r on the order of 10 minus epsilon. It will come back to the ground state, G, by spontaneous emission in any possible direction. And since spontaneous emission is isotropic in all possible directions, the linear momentum loss in the emission process is equal to 0 on the average. So on the average, the momentum change of the atom, linear momentum change in the emission is equal to 0. It's not equal to 0 in the absorption process. So if you consider a cycle absorption spontaneous emission, which is called a fluorescence cycle, the velocity change of the atom is just due to the absorption process, and it is given by the recoil velocity h nu over mc. And if you put the number in this equation, you find that the recoil velocity is on the order of 1 centimeter per second, 10 to the minus 2 meter per second. That's a very small velocity. And this is why people neglected for a long time this effect, this recoil effect. But if the atom is in a laser beam, a resonant laser beam, after a cycle, it's still in the laser beam, so it can absorb a second photon and emit a third photon and fourth photon, and it can undergo a large number of cycles per second, which I can call W. And the mean number of cycles per second, what is the order of magnitude? Since each cycle has a time which is limited by the time spent in the excited state, tau r, within a factor 2, the order of magnitude of W is 1 over tau r, because each cycle lasts a time of the order of tau r. That means that since tau r is on the order of 10 minus 8, the atom can undergo 10 to the 8 cycles per second, 100 million cycles per second. Now I can ask the following question: what is the mean velocity change per second? Not per cycle, per second. And in physics, the velocity change per second is what we call the acceleration or the deceleration. Velocity change per second, per unit time. So the acceleration, the mean acceleration or deceleration of an atom is the velocity change per second. It is the velocity change W per cycle times the number of cycles per second. We recall delta V is 10 minus 2. W is 10 to the 8, so you get an order of magnitude of 10 to the 6 meter per second squared. And as you know, the acceleration due to gravity is 10 meter per second squared, g, what is called g. So you see that an atom in a resonant laser beam feels an acceleration or a deceleration of 10 to the 5 g, 100,000 times g. And that's a huge force. You know that a cosmonaut in a rocket feeling an acceleration of 2 or 3 g is uncomfortable. Okay? So this is 100,000 times bigger. That means that an atom in a resonant laser beam experiences a force which is huge, which is 100,000 times more intense than the gravity, and which is called the radiation pressure force. Now, using this force, you can slow down and cool atoms with laser light. And the notion of slowing and cooling are two different notions in physics. The velocity distribution of an ensemble of atoms has a mean value and a dispersion around the mean value. Decreasing the mean value is what is called slowing down. Decreasing the velocity spread around the mean value is what we call cooling down, because in physics, the temperature is related to the disordered motion of atoms, which correspond to a velocity spread. And by using radiation pressure forces, one can cool atoms and slow down them. And before explaining the mechanism, let me just give you the result. It's possible now to cool atoms to a few microkelvin, where they have a velocity on the order of centimeter per second, even less, a few millimeter per second. To have an idea of what it is, you compare this with room temperature. In this room, the temperature is about 300 Kelvin, and the velocities of the molecule of nitrogen, of oxygen, are on the order of kilometer per second, a few hundred meters per second. So you see, you go from 300 Kelvin to 10 minus 6, you gain a factor of 300 million, and you reduce the velocity dispersion by a huge amount. So it's a big step to low temperature. So let me explain first how it is possible to stop, to decelerate atoms and to stop them. The idea is simple. You take an atomic beam coming from an oven, atoms propagating with a velocity of 1 kilometer per second, and you irradiate them with a laser beam counter-propagating. And the radiation pressure exerted by the beam slows down the atom, as shown in the movie you showed just recently. You have photon impinging on the atom, and the atoms are progressively slowed down. And the deceleration is 10 to the 6 meter per second squared. If you start with 10 to the 3 meter per second, you stop the atom in a time which is 1 millisecond. In 1 millisecond, you stop the atom, and during this time, they travel over a distance which is given by a high school formula, V naught squared divided by 2a, which is 0.5 meter. That means that in a laboratory experiment, you can stop an atomic beam with an initial velocity of 1 kilometer per second. Of course, you have immediately an objection that as soon as the atoms start to decelerate, because of the Doppler effect, if they are initially in resonance with the laser light, they will get out of resonance and the force will decrease. And that came a very nice idea of my colleague Bill Phillips, who got the Nobel Prize in the same year as me, was to put a magnetic solenoid around the atomic beam with the number of terms here decreasing with the distance to produce an inhomogeneous magnetic field gradient along this direction. And it turns out that the magnetic field shifts the spectral line by an effect which is called the Zeeman effect, and you can calculate the profile of the beam so that when the atom moves here, the change of the atomic frequency due to the Zeeman effect compensates the change of the apparent laser frequency due to the Doppler effect, and you maintain the resonance over the whole trajectory at the maximum value, and then you can stop the atom. And the next slide shows you, for example, a picture, a real picture. Here, that part is the last part of the solenoid, that stray light, and this picture here is the fluorescent light emitted by the atomic beam, and you see that the atoms are coming from the oven, and they are stopped here, and they come back here. And that, by your eye, you can see the atomic beam which is stopped and which comes back to the oven. Of course, now with laser diode, we can also charge the laser frequency of the diode to maintain the laser condensation. It's even simpler. Now, let me explain the simplest cooling scheme, which is use the Doppler effect and which was suggested by all these people. And the idea is to use, instead of a single laser beam, 2 laser beams, counter-propagating with the same intensity, the same frequency, new laser, smaller than the atomic frequency, slightly detuned to the red. So what happens for an atom moving along this axis? If the atom is at rest, there is no Doppler shift. The 2 apparent frequencies are the same. So this force is equal to this force, and with opposite sign. So the 2 forces cancel out, and the net force, the total force, is equal to 0. If the atom is moving to the right, like that, because of the Doppler effect, this frequency will be shifted up, and this frequency will be shifted down. If this frequency is shifted up, it will get closer to resonance. More photons will be absorbed from the counter-propagating laser beam, and this force will increase. In this case, the laser frequency will be still farther from resonance, less photon will be absorbed, and the force will decrease. So you see that as a consequence of the Doppler shift, the 2 forces will no longer be balanced, and the net force will be determined by the counter-propagating laser beam. It will be opposite to the atomic velocity, and for low enough velocity, power series expansion shows you that the force is opposite to the atomic velocity and proportional to V for V small. So you have a viscous force. You know that when you have a pot of honey, and when you try to move a spoon in the pot of honey, the faster you move the spoon, the greater the friction. It's called viscosity. Here we have the same thing, and this is why the people who observe this effect call that optical molasses. You have like a pot of honey, but instead of honey, it's a light which plays the role of a viscous medium. And for example, here you have an example of optical molasses at the intersection of 3 beams, because here you cool the atom along this axis, along x-axis. You take 2 beams along y-axis, 2 beams along z-axis. You have 6 laser beams, and you can cool all 3 components of the atomic velocity. Now, you can make the theory of this effect, And when you make the theory of this effect, you predict that the temperature you expect is on the order of 200 microkelvin, which is very nice already. But when people started to try to measure this temperature accurately, and that's not easy because how can you measure temperature for a gas as low? They found that the temperature was about 100 times lower. Usually in physics, when you make an experiment, you find a result which is less good than what you expect from theoretical calculation. Here it was better. So it was a good surprise. And the reason what happened. And before explaining what happened, let me explain to you how one can measure such temperature. We use what is called a time of flight technique. We start with the molars here, and at time t equals 0, we switch off the laser beam. So the atoms are no longer held by the laser beam, and they start freely forming a shower. And we put a laser beam a few centimeters below to detect the time at which the atoms which are released cross the laser beam by looking at the fluorescence line. They emit when they traverse the beam. And each trajectory is a parabola which determines on the acceleration due to gravity that you know, which depends on the position distribution of the atom, which you can determine by taking the picture of the molars, and which is also depending on the initial velocity distribution, which characterizes the temperature, and we want to know. So, assuming a certain velocity distribution, you can calculate the time of flight signal, and by comparing with experiment, and by fitting the two curves, the theoretical and you can measure the width of the velocity distribution and determine the temperature. And it is in this way that for the first time, my colleague Young-Philippe found that the temperature was about 100 times smaller than expected. And the reason for that was found in our laboratory in collaboration with my young colleague Jean Dalibar, and the following idea. The idea is that atoms in the lower state have a structure, a spin structure, spin up and spin down. Alkali have many sublevels. One of the pictures you showed the hyperfluorescence. It's even more complicated, but let me explain it on a simple case of a spin 1/2 system. So you have two spin states. When you have two current laser beam, counterpropagating laser beam, they interfere and they give rise to a standing wave with maxima, antinode, and node minima of intensity. So the intensity of the light is specially modulated. And the polarization of the light is also specially modulated. And since in laser cooling the light is not resonant, you have light shift. And then we come back to what I explained just before, light shift. So that means that the two spin states are spatially shifted. They are shifted in a spatially dependent way. And they are not shifted in the same way because the probability of the transition starting from spin up and spin down are not the same. So you have a spatially modulated light shift of G plus and G minus, and correlated spatial modulation of optical pumping rate, because the light is not detuned too far, and atom can absorb light from one demand sublevel and fall down in the other demand sublevel, which is exactly what is optical pumping. And you can achieve a situation which are represented here, that, for example, the spin down state, the position of which is modulated, that's the spin up state, position modulated, with a spatial period which is the wavelength of light. And you have optical pumping transition from one sublevel to the other, from one sublevel to the other. And you can have a situation where the atom starting from the bottom of a valley here, climbs a potential hill, moving to the right, climbs the potential hill and reaches the top of the hill, where it has a large probability to be optically pumped in the other state, that is to sit to the bottom of the valley, and from there it climbs again, optical pumping to the bottom of the valley, and you see that the poor atom is exactly in the situation of the hero of the Greek mythology, Sisyphus, who was condemned to roll up a rock to the top of a mountain, and when he was at the top, the gods were putting him back to the bottom. He had to do again the job, and again, and that was exhausting for him. And this is why we call this scheme Sisyphus cooling. And you can make the theory like that. You see the poor atom is climbing, going down, climbing, and that cools down the atom, it reduces its energy, and you can make the theory of this effect and show that it exactly explains the whole set of experimental results. And we did experiment also in Paris to demonstrate the validity of this method. We also devised another cooling scheme which was able to cool atoms down to the nanokelvin range, but I have no time to explain it now. Let me finally explain to you how it's possible to trap atoms, to confine them in a small region of space. And here again, we use light shift by using a focused laser beam. We take a laser and we focus it strongly, and you see that the intensity of the laser beam will be maximum at the focus of the laser beam. And suppose that we detune the laser beam to the red, omega L smaller than omega A. And you remember that in this case, the light shift is negative. So if you cross the laser beam along any direction, here for example, you see that the energy of the ground state will decrease proportionally to the intensity. The decrease will be maximum here, and it will increase again. And that for all possible directions. So you see that the energy of the ground state as a position of space will be minimum here, so we'll have a potential well for the atom. And you can trap atoms in this potential well if they are slow enough, cold enough. And that is what is called a trap. And it's efficient for cooling atoms, neutral atoms, if they are cold enough. And in fact, that can work even for biological objects like viruses or bacteria. You can trap by such object by focusing laser beam. You can catch them at the focus, and by moving the laser beam, you can move this object. This is what is called now optical tweezers. It's a useful tool in biology. There are other traps which have been devised, which I have no time to explain. And also, there is another scheme which was extremely useful in this experiment. Once the atoms are very cold in the trap, they can collide together and lead to evaporation. Suppose that you have atom in a trap, and suppose that two atoms with initial energy E1 and E2 collide and undergo an elastic collision. In an elastic collision, they get new energy, E3 and E4, such, because of conservation of energy, E3 plus E4 is equal to E1 plus E2. If E4 is greater than the depth of the potential well, the atom with E4 escapes from the well, it leaves the well. The remaining atom has a much lower energy because of conservation of energy, and by colliding with the other atoms, the whole sample cools down. This is exactly what you do when you blow over your cup of coffee or tea. You evacuate the hot molecule, and the remaining molecules are colder. And you lose atoms in this way, but the sample cools down more efficiently. And by this technique, following laser cooling, you can reach easily now temperature of nanokelvin, in a nanokelvin. Just to give you an idea, I have represented here a picture of a bulb, a Pyrex bulb of half a liter containing cesium vapor. The cell is at room temperature so that you can keep it with your hand. And in the middle, you apply laser beam. And in the middle of the cell, you see this orange spot here is a ball of about 100 million atoms, cesium atoms, which are trapped in the center of the cell at a temperature of 1 microkelvin. So you have a very nice device you can keep by hand at room temperature. In the middle of the cell, you have a sample of 100 million atoms at 1 microkelvin. And that shows you an example of what an experimental setup looks like. That the Zeeman slower for slowing down the beam, that the trap here, and that all the optical components allowing you to produce a laser light with diodes, to polarize it with laser beam, lenses. That looks complicated, but in fact it can be managed by 2 people, 3 people. It's a small scale experiment compared to the high energy experiment at CERN or the big accelerator. Now, I switch to the last part of my talk. What can you do with ultra-cold atoms? Why they are interesting? What kind of new research field, new application? And I would like just to give you a brief idea. First, slow atoms, cold atoms are slow. So you can keep them in the observation volume for a very long time, compared to thermal atoms, which moving at 1 kilometer per second, spend a very short time in the place where you observe them. And in physics, the longer you observe a system, the more precise the measurement you can perform. There is some sort of energy-time uncertainty relation. So with cold atoms, You can make precise measurement of atomic frequencies, and you can use this atomic frequency for making clocks, unit of time. You can make multi-atomic clocks. That's first application. Second application, you remember that the de Broglie wavelength is lambda de Broglie equals h over mv. V is in the denominator. Small v means large de Broglie wavelength. So with cold atoms, the wave aspects of atomic motion are much easier to observe and to detect. And you can repeat with de Broglie waves all the interference diffraction experiment usually done with optical waves. And the new research field have been found called, for example, atomic interferometry. It's interferometry with de Broglie waves and not with optical waves. And finally, when the density of the sample is high enough, more precisely when the mean separation between two atoms in the sample becomes on the order of the de Broglie wavelength or smaller than the de Broglie wavelength, the wave function of the different atoms start to overlap, they interfere, and this gives rise to a phenomenon which was predicted by Einstein following the work of Bose in 1924, predicting that at a sufficiently low temperature, all atoms should condense in the ground state of the trap which contains them. So we'll have 1 million atoms all with the same wave function. You have what can be called a macroscopic matter wave. And that is what is called Bose-Einstein condensation. And in the slide shown by your colleague at the beginning, just before my lecture, you have seen such a nice picture of this condensate. So let me explain to you briefly what is a clock. You know, everybody has a watch with a quartz. A clock is an oscillator, a quartz. But if you take a quartz, two quartz, they have not the same frequency. They are not universal. And if you take a single quartz, as a function of time, its frequency jitters. They are not the same frequency from day to day. So to have a precise clock, you have to take a quartz and to stabilize its frequency, to stabilize on a standard. And if you stabilize the frequency of the quartz on an atomic frequency, this is what is called an atomic clock. So the principle of an atomic clock, you have a quartz oscillator generating an electromagnetic wave which drives the transition between two energy levels of an atom. And in fact, the international definition of the second, the unit of time, is done through a microwave frequency transition of the cesium atom. So atomic clocks use cesium beams. And you look at the central frequency of this transition, and with the servo loop, you correct the frequency of the quartz to maintain it at the center of this line. In fact, every atomic line has a center frequency, nu naught, and a certain width, delta nu. And it's clear that the smaller delta nu, the narrower the line, the better will be the lock, the stabilization, and the better will be the clock. Okay? So to make a good clock, you have to find a narrow atomic transition. But as I mentioned to you, delta nu is inversely proportional to the observation time. The longer you observe the system, the narrower the resonance line you can observe on it. So the better the clock. Cold atoms moving slowly allow you to get long observation time, large value of t, so small value of delta nu, and very precise clock. Okay, that's the idea. Simple, very simple idea. And how this is done? This is done in the following way, using what is called atomic fountain. You take a ball of cold atom, a molar, and with a laser pulse, you throw them like that, upward. And you make what is called a fountain. Atom goes up and down by gravity. Like a fountain, except instead of water drops, here you have atoms. And the atoms pass once through the cavity which measures the frequency, once on the way up, and once on the way down. Now, if you have a usual clock using a beam of 1 kilometer per second, crossing observation zone which can be much bigger than 1 meter, you get an observation time of 1 millisecond. 1 kilometer, 1 meter, 1 millisecond. In this case, you see, the time it passed through the cavity can be of the order of 0.1 second. So 100 times longer. So you get immediately 2 orders of magnitude better accuracy. And that's an example of the resonance curve you can get on the clock. And with this clock, which is achieved, for example, in Paris by my 2 colleagues, Christophe Salomon and André Cléron, they have achieved the best atomic clock in the world, having a frequency stability of 1.6 10 to the minus 16 for an iteration time of 5 10 to the 4 seconds, and an accuracy of 7 10 minus 16. To give you an idea, that means that if you have a clock like that starting at t equals 0, 300 million years after, it will be off by less than 1 second. That gives you an idea of the accuracy of the clock. And with such clocks, you can improve dramatically the accuracy of the GPS system, because the GPS system uses atomic clocks in satellites to determine the position where you are in the Earth. You can improve very dramatically the accuracy with which you can synchronize pulses going through high speed internet information going through a fiber. You can also, of course, perform very interesting tests of general relativity, because 2 clocks at different altitude do not exhibit the same time because of the gravitational redshift. So you can make a lot of basic physics with such high precision clocks. And of course, you can be tempted to throw the atom higher and higher to increase the observation time, but that's not sensible because you have to shield the magnetic field of the Earth over a long distance. It's not easy to make a 10 meters high fountain. So the best idea is to go to space, to get rid of gravity, because if you have no gravity, if you have cool atoms, they remain there moving with velocity of 1 millimeter per second. So we started in France a series of what is called 0G experiment. In fact, the experiment is done in a jet, a Caravelle or an Airbus. The pilot starts in ascending phase like that. He switches off the engine, so the plane is free. It makes a free fall parabola, and when the plane falls down like that, the pilot switches on the engine again. It makes a second parabola, and so on. Each parabola lasts about 20 seconds, and that runs during 2 hours. And in the plane, there are about 20 groups doing experiment, 0G microgravity experiment. Of course, if you are sick at the beginning, you are really sick during 2 hours. Only young people are admitted. I was not admitted to do the experiment, but my colleague did it. And the next slide shows you the cold atoms groups here floating in space during one of these parabola, and that's the equipment here. And the experiment shows that it's possible to maintain the frequency of the laser in good way and to do the experiment in this condition. So our project now is accepted to fly, hopefully in 2007, in the space station. Here you will have a clock with cold atom in a space station, delivering time to all clocks in the Earth, synchronizing all these clocks, and also making a very precise test of fundamental theory. So that's a project which I hope will run out. So you see, it's a dramatic improvement. Now the improvement with respect to space clock, usual space clock with thermal atom, is a factor 1,000 more precise than all existing clocks. So now, second application, interference between the Broglie waves, and I would like to briefly describe one experiment which was done by 2 Japanese colleagues, Shimizu and Takuma in Tokyo, which is very beautiful. These people took a cloud, a morass of cold neon atom, cool in a metastable state, an excited state with a very long lifetime, about a few minutes. And they switch off the laser beam, so the atoms fall through a screen with 2 slits, and here an observation screen. It's exactly the replica of the experiment I showed at the beginning, except now you use atoms and not light. And when an atom hits the plate, since it is in metastable excited state, it has a huge internal energy, and when it hits the plate, it's a lot of electrons you can detect. And I seen this experiment in Tokyo. I know, so the movie and experiment is spectacular, because when you see the screen, you see one atom, one bright spot here, spot here, spot here. At the beginning, it's really random. And when you accumulate, this is what you observe. You observe a set of points here, Each of these points is the impact of an atom, a single atom, but you see clearly that you have places where you have a lot of impact and places where you have less impact. You see interference fringes. So you see that each atom gives rise to a localized impact, but the spatial repartition of the impact is spatially modulated. And you get exactly something similar to Young fringes, and when you calculate the interfringe by the Young formula replacing the wavelength of light by the Doppler wavelength, you get exactly the correct value for the interfringe. And I like very much this experiment because it clearly exhibits the wave-particle duality for atom. Each atom is a particle. It gives rise to a localized impact. But at the same time, each atom is associated with a wave, because if you have no wave, you have no interference. And the connection between the two, the particle and the wave, is probabilistic. The waves gives you the possibility to calculate the probability that the particle manifests itself. That's the Born interpretation of the wave function. And now this experiment is used in all standard mechanics, quantum mechanics lectures for students, because it really exhibits a real experiment which exhibits the wave-particle duality for matter. Of course, I have discussed here a simple experiment, but you have more complex experiment where you can take two de Broglie waves circulating in opposite direction in a loop, like that and like that. And if the platform is rotating, you get a shift of the interference fringe, which is proportional to the speed of rotation. You make what is called a gyrometer using the so-called Sagnac effect. And de Broglie gyrometers using de Broglie waves are expected to be orders of magnitude more sensitive than laser gyrometers using light wave. Of course, the technology of matter wave is not yet as developed as laser light, but even now, the most precise gyrometer is using de Broglie waves, and it can detect angular rotation speed 10,000 times slower than the speed of rotation of Earth. The Earth makes a turn in 24 hours. You can detect rotation speed 10,000 times